So this is, in this picture you have another format like so we have this. Let's see, we have one. We have worker here. Actually, this space is a work center. This work center is manned by one person. Work center is actually defined as a place where one worker works. So this worker is working with 1, 2, 3, 4, 5 machines. So he works with 5 machines. Sometimes in most cases one worker work with one machine, but it can be that worker can work more than one machine. Inputs for the layout decision. So you have specification of objectives of the system in terms of output and flexibility. So we need to specify objectives of the system in terms of output, that is how much we are going to produce, and then flexibility. Flexibility is from which you are producing, whether you are producing number of items, and then you have to switch between each other. Estimation of product or service demand on the system. Actually, demand is one of the inputs for the decision of the output. So normally the attempt is to produce the demand. And then processing requirements in terms of number of operations and amount of flow between departments and work centers. So actually processing requirements is a very important issue, because maybe the same item need to be processed in the same work center or number of locations. And then space requirement for the elements in the layout. It says certain machines require larger space, so some machines require smaller space. So the space requirements, when we consider all the elements, let's say all the machines in the work center, what kind of a space?
So, excuse me, sir. Would you be able to re-explain what is that first flexibility as well as process requirement in terms of number of operations and amount of flow between departments and work centers? Point number 1 and 3, sir.
Flexibility is like if you are producing, let's say, the same using the same facility. If we are producing, let's say, a number of brands, and then we have to switch between the brands. For an example, Toyota company is using a scheduling technique in order to, they in the end they produce all the brands there according to the demand forecast, and they have switching system. So from you see, we are producing let's say brand A, B, C. Like let's say you produce 3 brands, and then so there are 2 options. One option is you can produce A and then stock that, and then produce B and stock it, and then produce C and stock it. And then from A to B, B to C, you have to switch, and then from C to A again you switch. That is so that is one approach. And then the other approach is like, you let's say you have you have let's say you have to produce A, and then you produce three A's, and then four B's, five C's, and then let's say four B's, three A's, four A's. You see, so like this, so here, you switch from A to B, from B to C, from C to B, and like you have small batches. Here it's three. A is a small batch of three, and small batch of four B, and then five of C. So here, this is a very flexible situation where you can switch from A to B, C to B to C, so and then come back to A again. So this is this is highly flexible. The other approach is that let's say you produce let's say 100, let's say 10,000 A, 10,000 A, and then after that you produce 20,000 B, and then let's say 5,000 C. So this method is not that flexible. So you are producing fairly large batches of A, B, C, and then you produce a large lot of 10,000, and then switch to B, and then you produce 20,000, and then switch to C, and produce 5,000, and then maybe come back to A. So this sequence is not much flexible. So this sequence is more flexible. You got it?
Thank you, sir. Then the next point, sir, the third one.
Processing require in terms of number of operations and amount of flow between departments and work centers. So is that the one?
Yes, sir, that one.
So let's say here, we think so here, let's say you have imagine a situation where you have so you see here, if you look at this diagram, in this diagram, let's say you have to let's say this is L, for example. L is one machine, okay, one work center, and then it goes to this M, work center M, and it goes to work center G, okay, and then again G. So there are 6 work centers for G, okay. So here and then for example this work center gets one M from here, another M from here. Okay, so then this work center has to process the inputs coming from this one and that one. Okay, so then let's say if it is let's say if it is two processing, so then the processing requirements here at G is it has to process two M's, okay, two M's, and then so the processing requirement of G here is need to process two M, and then let's say processing the two M also then here here G you get, let's say two operations. You get two, G needs to handle two operations, whereas M here one of the M's take this particular M, this M, it processes only one. It is one operation. It is also this one also processing, this M also processing one operation. So you see, like let's say for this particular M, it gets L to process, so it is one operation, and then this particular L coming to this M is also one operation. Here it is two operations, like has to process two inputs coming, so two operations. So that way we can say we can say the processing requirements in terms of number of units coming in. So that is one way, and also like within the machine, within the work center. Let's say, for example, this this particular person has to process the item using 1, 2, 3, 4 machines, right? So then the input coming, and then he has to use this machine, and then this one, and then that one, and then find this one. So then the output goes out. So that way also within a work center also you can specify let's say we can specify the kind of operation that the person in the work center has to do. So that is also another way, like within the work center, and also there are two ways. One way is in terms of inputs coming, and then in terms of the real work that has to be done on the input to get the output. That's also another. Got it?
Yes, sir. Thank you, sir.
Space requirements for the elements in the layout, like for example here, in this work center. As I told you, work center is manned by only one person, right? So then in order to house this the number of machines, he needs a space. Okay. Whereas this one is fairly, this machine. This one is a fairly big one. This one is a fairly big one. And this is also next bigger one. And then so there are two machines that are not so big. So you see, the big machines require a larger space, and then small machines require smaller space. So this is only one work center, right? But in order to produce an item, let's say motor car, for example, it has to go through several work centers. Not one work center. It goes through hundreds, more than 300 work centers. And then space availability, see, we need to, we cannot increase the space as we wish. Just like, you go to the shop and buy a bread, it's not that simple, right? So, space, the buildings, for example, to construct a building, it requires, you need to have a land. And then land is either you have to buy it or maybe you inherited it. So either way, both processes are, sometimes inheritance is more difficult to, maybe more difficult than the buying itself. So to really get the possession of the inheritance is a big issues actually in countries like us. So then, you need to buy a space, and then either way, acquiring the land, the land space is a big thing. And also constructing a building, also constructing a factory. Sophisticated factory actually will take 2-3 years. But then not so sophisticated, like garment factory, for example, is possible to construct within maybe 6 months. So you see, getting us required space is a serious matter. So the available space is what with what you have to arrange your work the facility. And then production layout formats, we have process layout, also called job shop or functional layout. And then we have product layout, also called flow shop layout. So this is arranged according to product layout. The production flow is arranged according to the very way that the product is produced, the steps of the production, production steps are the production flow. Okay. And then in the process layout, it's not the production steps, it is the functions, the kind of functions that is being served by a particular department. So, and then the concept of group technology, we call it cellular layout. This combines, advantages of process layout and product layout to arrive at a more flexible processing system. And then we have fixed position layouts. Here the layout is fixed actually. Project layout is a special case of fixed position layout. So these are some of the production layout formats. Process layout, we have been given interdepartmental flow. So given the number of moves to and from all departments. And then the cost of moving from one department to another. Existing or planned physical layout of the plant. So these are what we have, data we have. And then what we need to do is determine the best location for each department, where the best means maximizing flow, minimizing costs. Let's say this is an example of a process layout. And then this the red arrow is for one item. So that particular item starts its production from foundry and then goes to lathes, and from lathe to grinding and then to painting. And then the second item starts from forging and then welding, milling, and then painting. Forging, grinding, welding, milling, and painting. So second item. Third one starts from foundry and then goes through milling process and then painting. You see here, this in this process, production process, here we got 4. Red one, the green one, the blue one, dark green one, and then light green one. Light green one starts from foundry, drill, welding, milling, and then after milling, your output is finished, right? So then you have 5: red, blue, 2, and then dark blue, 3. This red one is 1. This is something like light blue. It is number 2, and then that is number 3, dark blue, and then foundry, drills, welding, filling is number 4. So here you see you have this production process. This layout is producing here. We got 4 items. 4 items are processed. And then these departments. Grinding is the department. So the function that the grinding departments do is grinding. And then painting is a department. The function that the painting department do is painting. And then forging department do only forging. Lathe departments do only lathe. Drilling departments do only drilling. Foundry department do only foundry. And then welding department do only welding. And then milling department do only milling. So like that, these departments, you have working departments, 1, 2, 5, 8 departments. These 8 departments are actually handling 8 functions, and then the office is there to handle the management aspect. So here you get 9 departments. Out of the 9, the 8 are working departments, and then 8 working departments handle 8 different functions. So this that's why we call this process layout Another way of calling is we call it functional layout. So then, this example, process layout example, you have, flow between departments, so number of moves, right? From 1 to 2, 175, 1 to 3, 50, 1 to 4, 0. This is, so number 1 is raw material storage department. Number 2 is cutting department. Number 3 is assembly department. 4 is sewing department. 5 is ironing and packaging department. 6 is ready-made storage department. 7 is administration. 8 is transport department. And then 1 to 2 is 175, 350, 40, 530, 6, 200, 720, 825. And then, the layout is, the current layout is 1, 2, 3, 4, 5, 6, 7, 8. So this is the current layout. Now, numbers indicate actually number of loads moved from, let's say, 1 to 2, 1 to 3, 1 to 4, and so on. Flow between, let's say, number of loads, right? And then cost rupees 10 to move a load between adjacent departments, and another additional 10 extra for 10 extra for each department in between. So if we are to work out the cost of this layout, you can work out the cost of this layout. Cost of the layout. Okay. Now you see, I'm going to work out from here. 1 and 2 are adjacent. So therefore, 1 and 2, cost between 1 and 2 is 175 multiplied by 10. So it's not possible. So I'm going to, let me do it in from 1 to 2 is 175, 50 cut 0. Can anybody, are you seeing this, this slide?
Yes, sir, we can see the grid.
Okay, so can you tell me the numbers? Okay, because you tell me the numbers. I'm going to enter the numbers in the Excel sheet, and then I will share the Excel sheet with you. You tell me the numbers, right? From 1 to 2. 1 to 2 is 135. 1 to 3 is 50. 1 to 4 is 0. So like that. Okay, tell me somebody. Okay.
Sir, 1 to 2, 1 to 2, 175. 1 to 3, 50. 1 to 4, 0.
1 to 5,
30. 1 to 6, 200. 1 to 7, 20. 1 to 8, 25.
And then 2
to 0, 2 to 3, 0. 2 to 4, 100. 2 to 5, 75. 2 to 6, 90. 2 to 7, 80. 2 to 8, 90.
90.
Then, yes, 90. Then 3 to 4, 17. 3 to 5, 88. 3 to 6, 125. 125, 125. 3 to 7, 99. 3 to 8, 180. Next, 4 to 5, 20.
20.
Yes, 20. 4 to 6, 5. 4 to 7, 0. 4 to 8, 25. Then 5 to 6, 0. 5 to 7, 180. 5 to 8, 187. Then 6 to 7, 374.
374.
Yes, 374. 6 to 8, 103. 103. 103. Then 7 to 8, 7 only.
And then department structure is 1, 2, 3, 4, 5, 6. One, two, three, four, five, six, 7. Okay. So here, now for adjacent department, cost is 1. Adjacent cost equals 10. And then other at 10 for every department in between. For an example, 1 to 2 is 10, 1 to 3 is 10, 1 to 4 is 10. And then 1 to 5, we have to pass through either 3 or 4. So then 1 to 5 is 20. 1 to 6 is again 20. 1 to 7 is, you have to pass 2 departments. So that is, for 10, you have to add 20. So then it's 30. 1 to 8 also 30. So that costs are so let's say 1 to 2, 1 to 2, 10. And then 1, 2, 3, again 10. 1 to 4, 10. 1 to 5, 20. 1 to 6, 20.
Why we took it as a 20? 1 to 5?
So, you have to pass, when you go to from 1 to 5, you have to pass either 3 or 4. Okay. So then where the costs are given, so for every department next to each other, cost is 10. And if you have to, for other departments, not adjacent departments, you have to add 10 more for each department that you have to pass, so in between. So then for when you go from 1 to 5, you have to pass 3 or 4. So then you have to pass one department. So that's why 10 is added. So 1 to 5 cost is 20. 1 to 7 is, you have to pass 2 departments. So then for the 10, you have to add 20. So then it becomes 30. And then 1 to 8 is also 30. Now, you see, we can like 1 to 2 is cost is 175 is number of loads. So you multiply this by multiply by 10. And then 1 to 3 is also 10 multiplied by 50. That's 500. So this is 1 to 5 is 20 multiplied by 30. 600. 1 to 6 is 20 multiplied by 200. That is 4,000. 1 to 7 is equal to 30 multiplied by 20. So that is 600. 1 to 8 is 30 multiplied by 25. So then 2 to 3, 0 multiplied by 10 is 0. And 2 to 4 is also 10 multiplied by 100. 2 to 5. So, you have to pass one more department. So, it's 20. 20 multiplied by 75. 2 to 6 also 20. Multiplied by 90. 2 to 7 is 30. Multiplied by 80. 2 to 8 is 30. Multiplied by 90. So, what to go is 10. Because, you can go to one, let's say, this one from 1 to 4, from this corner you can go. Therefore, it's adjacent. And then 3 to 4, 3 to 4, 3 to, for 3 adjacent, 5 is adjacent, 6 is adjacent, and 4 is also adjacent. So 3 to 4 equals 10 multiplied by 7. 3 to 5, 10 multiplied by 88. 3, 6 also adjacent. See, it's 10 multiplied by 5. Zero. The 3 to 8 is 3 to 7.
That is 20, no, sir. 3 to 7.
3 to 7 is 3 to 6. No? 3 to 6 is 10.
Yes, 3 to 7, I think 20, no?
20, yes. 20. Three to 6 is 10 next to each other. So it's 10 multiplied by 125. And then 3 to 8 is 20 multiplied by 180. And then 4 to 5, 4 and 5 are next to each other. 4, 6 also next to each other. And 4 to 5 is 10 multiply, and then this is 10. Okay. 4 to 8 is 20 multiply. And this is 5 to 7. 5 and 7, 5, 7 and 5, 8 are next to each other. So then we multiply by 10. This is equal to, so 5, 7 also next to each other. key source and street side. And then 7, 8 next to each other. So these are actually, so you see. So these are the costs, right? So we can add these numbers. And the cost, total cost equals. Get 35,270. So this is how, we calculate the cost of the layout, right? So 3 to 4 is 170. 3 to 4. Three to 4, we have 17 units, right? So then 17. Okay. So are there any other mistakes? So then the total cost of the layout is 34,740. So you see, let's say here from 1 to 2, 1 to 3, and then cost from 2 to also we can write down like that. From 3 to 5, 3 to 4, 3 to 6, also 3 to 7, 3 to 8. So we need to actually put them down. So we can put the cost also down in the same manner, same matrix, same matrix like that. So for the calculation purpose, like, when you can have a box, when you do the hand calculation, we can write down the cost, in the in the corner of the same box. Let's say this top left hand corner, you put the cost, and then you can put the load, in the right hand top right hand corner, and in the middle the cost. So then that way also, we can do the total calculation in the same table. So that, if you do it by hand. So this is how, we calculate the cost of the layout, okay? Total cost. So here we took, okay, number of loads to be transported between the departments, and then cost of moving one load from another department to one department to another department. So these were the two things: we number of loads multiplied by cost of moving a load. So we get the total cost of the layout. So if you have questions, you can ask. Any questions? In that case, I'm going to stop here in this one. We calculated the cost of this layout, right? So the product layout, also called a flow shop layout, is one in which equipment or work processes are arranged according to the progressive steps by which the product is made. So let's say if the product is made from, in this sequence, station 1, station 2, station 3, station 4. So this is, you see in this, the example we discussed, in this example, cost is 10 to move a load from between adjacent departments, and 10 extra for each department in between. So if you say cost is for 24 adjacent department, and then 10 extra for each department, say then from 1 to 2 is 20. And then 1 to 3 is 20. 1 to 4 is 20. Then 1 to 5 will be 20 plus 10, that will be 30. So then this cost is going to be 30 times 30, then that will be 900. So thus then numbers will change. Here, you have station 1, 2, 3, 4. So moving, so this is a sequential line, assembly line. Okay. And then technology, it's a transition from process layout. So then grouping parts into families that follow a common sequence of steps. And then identify dominant flow patterns of parts families as a basis for location or relocation of processors, physically grouping machines and processors into cells. So one of the advantages of the product layout is that, product layout is more efficient compared to process layout. So then process layout is is more flexible. So here you can process many products at the same time. In the product layout, you process only one product in one assembly line. Okay. So then it is more efficient. So then you take the advantages of product layout and process layout and develop the group technology layout. So product layout advantage is efficient. Process layout advantage is flexible. Okay, so you can produce more items in the same, with the same layout. So the method is grouping parts into families that follow a common sequence of steps. Identify dominant flow patterns of parts families as a basis for location or relocation of processors. Physically grouping machines and processors into cells. So this example, you can, you see, we have identified cells, this cell 1. For cell 1, we have grouped machine centers L, M, okay. And then for cell 2, MG, cell 3, LMD. So they're here. See, so then, this is the, the, within these cells, the majority of the parts are moving through the cell. Cell essentially function as a product layout. Okay, within the cell, the production process is a product layout. Okay, so that then we have increased the efficiency, but at the same time we are able to produce, let's say here we produce 3 items, okay. 3 items. 3 items, so let's say one marked in green, and then, so this green, what is happening in the cell, within the cell, is, this is more like a product layout. And cell 2 is also more like a product layout. Cell 3 is also more like a product layout. So, and then we get these items with faster production rate with the group layout, group technology layout, rather than let's say process layout. At the same time, we get the flexibility available in the process layout as well. So the method is, by grouping parts into families that follow a common sequence. Who is asking this question? If they give 20 rupees for adjacent department, then how much will be the cost of the layer? So in this example, in the previous example, we discussed actually the cost is the cost of moving one load from one department to another is considered. It's the cost may be labor cost. So then, here grouping parts into families that follow a common sequence of steps. So within the cell, identify dominant flow patterns. Process layout is, process layout is a functional layout, right? You see, this is a process example of process layout. And here, there are 8 departments doing 8 functions. Okay, so this is also called a functional layout. So here, the number of products produced are many, more than one. In the product layout, and also this in the process layout, different products, are produced with different sequences, okay, different sequences. So the process layout gets, you get different sequences for different products. So you produce different products, and then product layout, you produce only within a layout, only one product. For example, here in this product layout, you produce one product. So large batch of one product. So what is happening in garment factories? You have they are using the assembly, production, what they use assembly line, but then they cannot use the word assembly line because it is the fabrication is the main technology. Therefore, they call it a production line. So they produce, one batch is a large batch, maybe 100,000 units or 100,000 shirts of the same design. So like that. But let's say the group technology layout example, practically Toyota is doing it. Toyota is doing group technology layout so that, they produce, they have arranged their this method. So then Toyota production is going this way. They produce, let's say one brand, let's say they have stopped producing actually Toyota Premium. Let's say in the past, okay, let's say 3 Premiums and then Corolla Bs, then moving into let's say another one. So like that, they switch from, this is this method, this production method is possible only with group technology layout. This production method is possible with the assembly line. This is examples of assembly line. This situation is an example of group technology example when it comes to scheduling. And then, we're going to fixed position layout. Fixed position layout, the product remains at one location. Arrange materials and equipments concentrically around the production point in their order of use. Examples are, rockets, ships, movie lots, airplanes. For example, ships, in the dockyard. When one ship is built, it is thrown into the sea, and then the next one starts. So the ship is a big one, so all the equipments, machineries needed to produce the ship is around the ship, okay, around the ship. So those the layout is fixed. Layout is fixed. Here the product moves. Airplanes also are same method. So layout is fixed. Once the product is produced, it's taken out. And then we have the next method called project layout. So then the product stays once the project, let's say, examples are buildings, dams, highway constructions, sites. These are, once these are projects, okay? Once the project is completed, the product stays, but the project moves, the layout moves. For project, for that matter, you can say layout. So here, in this method, once it is completed, product stays, the project, that is layout, moves. The arrangement of components in one shot situation. So buildings, dams, highway constructions, these are some examples for projects. And then service layouts, we have retail service layout, office layout, warehouse layout, supermarket layouts, and so on. So each of these layouts, for example, retail service layout, layout is designed to maximize the sales, okay, sales. And then office layout, the main purpose of office layout is to maximize the supervision. Maximize the supervision, and also maximize the interactions, maximize the relationships. So these are the objectives of office layout. And warehouse layout, the safe storage of items is main purpose. And then the second main purpose is like when items are withdrawn from the layout, the withdrawal, issuing items from the layout is easy. For an example, if you had been to these people, the Rosell layout, Rosell warehouse in Narayanpeta, if you have been there, you must have seen how long it takes, to get your order. It takes a lot of time for these people to find out, your order, and then so the locating where in a large layout, where large warehouse, where so many thousands of items are located. So locating the item where it is actually should be easy in these warehouses with these warehouse people. Some people with a lot of experience, they know by heart which item is where, so that is other but the better recommended thing is, even for a new worker, finding the particular item where it is, that way it should be easy to locate it. And then supermarket layout, it is to facilitate or maximize sales. It's similar to retail service layout. And then in the supermarket, there are things like when a customer, you see, the layouts normally are designed in a manner that according to customer shoppers list. So then customer, there are items that are in the customer's shoppers list. And there are other items that when the customer sees, he buys. For example, buying chocolate, candy, and things like that. So they are normally not in the shopper's layout. Normally in the shopper's layout are main items like rice, and then meat, fish, vegetables. And then, so like, main items that are and washing powder, washing liquids, the soap, and the books and all. And so, such things are normally in the shopper list. So when the shopper goes to find those items that are in the shopper's list, we have to make sure that the layout should be designed in a manner that shopper will see other items that are not in the shopper's list are visible to customers, so that after seeing it, customer will put the item in the item in the cart. So and also that is one way, that is locating particular types of items is one thing. The other thing is selecting the shelf. So the most important items normally should be located uh, so that anyway the customer will search for it. But other items that are not in the shopper's list should be in the visible area. So like, for example, middle eye level shelf should be allocated for items that are not in the shopper's list. For items that are in the shopper's list, other levels, the top level and also the bottom levels can be used. Eye level shelves should be allocated to items that are not in the shopper's list. So that way, supermarket can maximize sales. So this ends the layout planning. Then I'm going to give you a break. After the break, we will start with assembly line balancing. So we meet in half an hour's time.
Thank you, sir.
Okay, are you all back?
Yes, sir.
You see, earlier we discussed types of layout also, and the process layout. Process layout is the very most common layout. You know, for an example, hospital has a process layout. The bank layouts in the banks are process layouts. Restaurants, you know, all these many places which resembles a job shop are process layout. And also the workstations in the process layout are specializing in a particular function. For example, in a hospital, you have wards, you know, the wards are classified surgery wards and, the physicians wards, gynecology, like that, you know, wards are classified according to a particular illnesses. And also you have X-rays, X-ray department, scanning, X-ray, like that, various functions are, for are also there. So you see, a hospital is actually a complex example of a process layout. So banks. Branches of a bank, even head office, even office, all kinds of offices are also process layout structures. The assembly line is a product layout structure. The main thing about assembly line is, it is created to facilitate mass production. So we discussed assembly line types, line balancing problem, steps in assembly line balancing, reducing task time. So these will be the topics that we will discuss. So the assembly line refers to progressive assembly linked by some material handling device. So material handling device may be a belt or forklift trucks, or maybe humans, so like that. For an example, in garment factories, if you have visited garment factory, you must have seen that, the work done in the previous stages passed down. Sewing stages are passed down. The person who does it gives it to the next stage by hand. And the present and allowable processing time is equivalent for all workstations. So this is one of the main differences between process layout and the product layouts, the assembly line for that matter. In the process layout, processing time is not the same for all workstations. In an assembly line, processing time is, especially the allowable processing time, is equivalent or equal for all workstations. Differences among line types, material handling device, belt or roller conveyor or overhead crane, these are one production line or one assembly line can differ from another the way that material handling is done. Examples: belt, roller conveyor, overhead crane, by hand, like that. Okay. And then line configuration. Difference between allowable time and that one I will discuss when it is coming in this lecture. And then line configuration, you can have a shape, a straight line, branching, different kind of configurations. Because of the variation in the configuration also, you can have different assembly line. And the pacing. Pacing can be done mechanically or by human. And then product mix, one product, multiple products. Workstation characteristics, worker may sit, stand, walk with the line or ride the line. And length of the line, a few or many workers. So like that, there are differences among the production or assembly lines. So this example, you have, this is a straight line, assembly line. This one is a straight line and this one is a U-shaped one. U-shaped one, this is a straight line. Actually, U-shaped assembly lines are used, let's say in this one you have 10 workstations. It is manned by 3 workers. For an example, in large universities, registration is done in 1 week. Registration is handled with a U-shaped assembly line. Assembly line balancing problem, assigning all tasks to a series of workstations so that each workstation has no more than can be done in the cycle time, and so that idle time across all workstations are minimized. You see, in the previously we said that allowable time. Allowable time is actually the cycle time. Okay, cycle time. Actual processing time in a workstation is, the present time. So cycle, you have to function within the cycle time. Cannot go beyond the cycle time. So within the cycle time, you have to process all your activities and pass down to the next workstation. So we have.
What is cycle time, sir?
Cycle time is, we discussed early also in the process analysis. Cycle time is, the time between producing the subsequent,
right, sir. I can remember that. The same cycle time here, no, sir?
Yeah, same.
All right, thank you, sir.
Time between, the
2 processes.
No, time between, the one, let's say item 1, 2, 3. So then, the time between the items, so the subsequent items. Let's say the time between 1 and 2, 2 and 3, 3 and 4, that's cycle time. So it should be equal. That is, all items should be processed within the cycle time, within workstation. And then, this example, this is a, toy wagon car. So position rear axle support, insert axle. So position rear axle support, it takes 45 seconds. This is not going to have any preceding task. And insert rear axle, it has to be done after A. It takes 11 seconds. And then tighten axle support screws to nuts. So it's done after B. And then position front axle assembly. So it is a starting activity. That's why it doesn't have any preceding task. And then E is 15 seconds, tighten front axle assembly screws. And then so it's followed by D. And then F is 12 seconds per position rear wheel 1, it's followed by C. G is 12 seconds, position rear wheel 2, then it's followed by C. H, position front wheel 1, followed by E. I is position front wheel 2, followed by E. J is position wagon handle shaft on the axle assembly, so then it's followed by F, G, H, I. And then final task is K, tighten bolt and nut, it's followed by J. So the total time for all tasks is 195 seconds. You get 195 by adding all these like 45 plus 11 plus 9 plus 50 plus 15 plus 12 plus 12, 12 and so on. So then, we need to specify the sequential relationship among tasks using the precedence diagram. Okay, the notation for the precedence diagram is the circle denotes the process or activity, arrow denotes the precedence. So then, here you have A is the starting one, B follows A, and C follows B. So then that's that sequence we draw. And next, we have D. E is done. D is a starting activity. E is done after D. And then F, G, H, I. F, G follows C, and then H, I follows E. And then J is done after completion of G, H, I. K is the final task. It's completed after J. So this is the sequence. And then, the times taken for each unit is written near the task. So this is what we call precedence diagram. And then we need to determine the workstation cycle time. Cycle time C equals production time per period divided by output per period. So then production time, in the day you have 420 minutes, that is 7 hours, multiplied by 60 seconds, so that you get 25,200 seconds, and the demand of the day is 500 wagons. So then you have to produce a wagon every 50.4 seconds. So this is the cycle time to produce 500 wagons in 420 minutes. Cycle time is 50.4 seconds. And then determine the theoretical minimum number of workstations required. And then, sum of the task time. To complete all the tasks, it takes 195 seconds. And then when you divide that by the cycle time, you get, 3.97. So, we can't have fractional workstations. So you need to round up, and then when you round up 3.97, even if you get 3.02, you have to round up to 4, okay? Because that fraction also has to be completed. So then the theoretical minimum number of workstations is 4. And then we need to Simon rule. So let's say we can, these are actually heuristic. We can select a primary rule as assign task in order of the largest number of following tasks. So that is, when you say largest number of following tasks, that means, the whole idea is to minimize number of tasks to be completed. And then tie breaking, assign task in order of the longest operation time. So the second rule, when you complete the longer operation time task early, that means your job will be completed early. So then if this task, if you write down the task, A has number of following tasks, you can look at the diagram. A has following task, you calculate 1, 2. A has B is 1, B, C, F, G, J, K. So then 1, 2, 3, 4, 5, 6. On the other hand, the other starting task, D, has following task E, H, I, J, K, that is 5. So if in the priority rule, the task with the most number of following tasks, the priority is given to A. So one thing is that when you select task for allocation of workstations, there are two conditions. One condition is the task should not have predecessors which are not allocated already. So if there are preceding tasks, you cannot allocate the task. So then a particular task should be either starting or the task whose predecessors have been completed. So then if we have priority rule, primary rule, the task having the most number of following tasks. So then A is allocated to the first workstation. So then, we can calculate who are the candidates. So the candidates will be B and D. B and D. And then B has following task 1, 2, 3, 4, 5. On the other hand, D has not been allocated. D also has 5 tasks, E, H, I, J, K, that's 5. So then we have a tie break with regard to number of following tasks. So then B and D are in a tie, but then the task time is 50 seconds, which is greater than B, 11 seconds. So we give priority, we do the tie break with the second rule, that is longest operation time rule, so that, D is allocated. So, we now selected the assignment rule. Then assign task to workstation 1, 2, etc. in sequence. Keep assigning tasks to a workstation, ensuring that precedence is maintained and total work is less than or equal to the cycle time. So we cannot exceed the 50.4 seconds. So if in that particular rule, let's say station 1A, task time is 45. And then from 50.4 seconds, we subtract 45. Then remaining time in the workstation will be 5.4 seconds. And then the candidate, there are two candidates possible after A, that is B and D, but B's time is 11 seconds. So then there are no tasks that can be allocated within 5.4 seconds. Therefore, 5.4 seconds is going to be idle. So there are no, that's why, feasible remaining task is none. And then the second station we allocate D, its time is 50, and 50.4 minus 50, then 4.4 seconds remain, and then feasible tasks are none. So therefore, we close the station 2, and then we start station 3, and then for station 3, we get B be having, you know, the number of following tasks 5. So B has following tasks 5. Then the other candidate is E after D. That is, E has 4 tasks. So therefore, B is selected. B is selected. And so that's why we have allocated B. And then you have E and C candidates. So E and C candidates, so you see, E and C candidates, and then E has E has 4 tasks following, and C also has 4 tasks following. So a tie break. So in the tie break, we use the longest operation time rule, and then we allocate E. And then after B allocation, you know, out of 50.4 seconds, 11 seconds allocated, then remaining time will be 39.4 seconds. And then E's time is 15 seconds. And then 39.4 minus 15, you get 24.4. The feasible tasks are CHI. And then C has more following tasks, that is 4. And then C is allocated. And then remain 24.4 minus 9, you get 15.4. The feasible tasks are F, G, H, I. And then F is allocated. So if I go back to the diagram, see, let's say we have once you know, actually, if we can work this thing out in the same page, workstation, like let's say, workstation, task, remaining time, and feasible task. So then, if you look at the diagram, you see A and D are the initial candidates. So then A has 6 following tasks and D has 5 following tasks. So A is selected for workstation 1. So we select A and its time is 45. So then 45 seconds. And the remaining time is 5.4. Feasible tasks are none. So, and then we have to separate. 5.4, you got like, its cycle time is 50.4 minus 45. That's how you got the cycle 50.4. Okay. So this will be idle because there are no feasible tasks, none. Therefore, this 5.4 is going to be idle. So next, the candidate is once A is allocated with more followers rule, you have a feasible task, B and D, that's candidates for workstation 2 are B and D. B has 5 following tasks, whereas D also has 5 following tasks, like 1, 2, 3, 4, 5. So then the D's time is 50, which is longer than B's time. Therefore, we tie break. In the tie break, D is selected. So we select for workstation 2. We select D, and then its time is 50, and the remaining time is 0.4. So this will be idle. And then feasible tasks, none. And then we have to go to station 3. Close the station 2. So then, for station 3, now A, D have been allocated. So then B and E are the candidates, and then B has 5 following tasks, whereas E has 4 following tasks. Therefore, we select B according to primary rule. So then B is selected. And then E's time is 11 seconds. So remaining time is 39.4. That is, you get that from 50.4 minus 11. Okay. Next, next candidate, feasible task after B or E. E is feasible. E is feasible and FG are also feasible. E is feasible. F, G also feasible. Out of them, most task with most follows is E. So then E is selected. 39.4, E's time is 15 seconds. 15 seconds. So 39.4 minus 15, then you get 15 seconds. Then you get 24.4. Feasible tasks, you get F, G, FG is feasible. After it was after, sorry, C. FG is not possible. After B, it is C, E, and C. E, C. After B, E and C. E and C are feasible. Out of them, E has 4, C has 4 following tasks, and E is also having 4 following tasks. E become feasible because D has been allocated. See, D has been allocated to workstation 2. So E is also feasible. And then E and C are feasible. E and C are feasible. No followers. They have both equal followers. Number of followers 4. And then out of them, task with longest operation time is E. So then that's why we select E. And after E is allocated, and then feasible tasks are C. C is feasible. H, I also feasible. H is feasible. I is also feasible. So then we have feasible task C, H, I. And then task with more followers is C. C. So then we allocate C. its time is 9 seconds. Time is 9 seconds. 24.4 minus 9, you get 15.4. Feasible tasks that are within 15.4. F, G, H, I. F, G, H, I. And then when we look at F, G, H, I, following tasks are, all of them have two. Two. So then task is more followers, F, G, H, I. Feasible also, F, G, I. Most followers also F, G, H, I. Longest operation time is also same. F, G, H, I. All of them time is 12. So we allocate, now you see there it's 12 seconds, 12, 12, 12. So we allocate in the here alphabetical order. You can allocate randomly, right? So here we allocate F. Its time is 12. And then what will remain 3.4. And feasible no. So then so this 3.4 is going to be idle. And then we go to workstation 4. And then you see we have allocated F. So GHI are feasible. And then we allocate GHI, you see, we allocate G. G. Time is 12. 50.4 minus 12 is 38.4. Feasible HI and then most followers HI. Same. Operation time is also HI. Same. HI. So we tie break with the alphabetical order. So we allocate H. Time is 12. Remaining time will be 26.4. And then we allocate feasible will be I. So then it's a single task. So we allocate I. Its time is 12. 26.4 minus 12 is 14.4. Feasible task is going to be J. FGHI all allocated. FGHI, so only J remaining. So you see, the most followers we select, let's say C has, after C, you have 1, F is 1, G is 2, J is 3, K is 4. Let's take H. After H, you have J, K, so then it's 2. After E, you have H, I, J, K, 4. So that's how, number of followers we decide. And idle or not, we decide whether if let's say if here 3.4, there are no tasks among the feasible tasks within the 3.4 time. So therefore nothing, so that time has to go to idle. So then J's time is 9, and then feasible task is J. So we allocate J. Its time is 9. 14.4 minus 9 is 5.4. And after J is only K. K is 9 seconds. So it is less than 5.4 is less than 9. Therefore, this is going to be idle. So feasible tasks, none. And then we go to station 5. K, its time is 9. Remaining time is 41.4. 50.4 minus 9 is 41.4. It's the last task, therefore feasible tasks are none. You see, this is this work that is in the node. This time is 8. Okay, J's time is 8, so then it's 8. It's 6.4. 14.4 minus 8 is 6.4. Then 6.4 idle. So then that's, this is what in the handle. So this is, it is this thing, that, we again worked out for explanation purpose. So this one. Right, so you have 5 workstations. So this, if you, in the precedence diagram, if we write down, if we box, the task to workstations, so it will be like this. So again, this one. So actually, what happens is so workstation 1 One you have A. So then you go to B, workstation 2. Task is T. So then workstation 3. Workstation 3 has DECF. Yeah. Next. Workstation 4. Task are GHIJK. IJ. Workstation, D is a starting task. So therefore, you have to allocate it before other tasks are allocated. So workstation 5. So it has K. So you see, so actually the processing sequence is this. Processing sequence is this, No, workstation is manned by one person. So then that person will well, this is, so we got this, 25,200. 60 multiplied by 60 multiplied by 420. 420 is 60 multiplied by 7. So you see, the working day is 7 hours. Actual working time is 7 hours a day. 7 hours equals 420 minutes. So 420 minutes we got 7 multiplied by 60. Multiply that by 60, you get, you get 25,000. So you see this sequence. So this sequence. And then, in the workstation, you have task A. In this one, 2, you have only D. And then workstation 3, you have B, E, C, F. And then station 4, you have G, H, I, J. Workstation 5, K. Okay, one task. So like, for example, if we look at these machines, in the previous slides, you saw, one workstation. There's one man working with about 4 machines. So let's say 4 machines are 4 tasks, okay. But then one man is working in 4 tasks, one man. So this is that kind of situation. So in this situation, there's one man, but he's working with 4. He's doing 4 tasks. Let's say to do the 4 tasks, he has arranged. We need to arrange 4 machines. Imagine 4, 5 machines. So like that. Okay. So but then the sequence is that. So it is in this particular sequence. The job is completed. And then efficiency calculation. Efficiency equals, sum of the task time. This is, the actual time for total actual total time for the task. That is 195 seconds divided by the allocated time for all tasks. So one workstation is allocated 50.4, and there are 5 workstations. So then 195 divided by 5 times 50.4, you get 77% efficiency. Okay, so 77% efficiency. And then there's another concept. We call it balance delay. So then balance delay equals delay equals idle time. Total time divided by total time available. So this equals total idle time equals total idle time in our first workstation. We have 5.4. Second workstation 0.4. Third workstation 3.4. Fourth one 6.4. Third one is 3.4. Fourth one is 6.4 plus final one is 41.4. So divide this by 50.4 multiplied by 5 workstations. tasks are divided to 5 workstations based on, you see, workstation time is maximum allowable time for a workstation is 50.4 seconds. And then we have to allocate these tasks for workstations within the 50.4 seconds without violating the precedence. Without violating the precedence. For example, B has to be done after A is done. So here, you know, precedence is not allowed to be violated. And also we are not allowed to allocate tasks to workstations more than the cycle time. So cycle time is 50.4 seconds. So when we do that, you know, we arrived at 5 workstations. So that's how you get 5 workstations. And then, you know, this one, when we simplify it, what is 57 divided by 252?
So the upper part altogether 57.
All right. 5.8 and then so when you divide that, you know, let's see. Five point four plus 3.4 plus 57 is divide that by 50.4 252. So then you get 0.226. 0.226. Point 226 equals, it is actually equivalent to it is equivalent to 22.6%. So then balance delay is 22.6%. And actually, yeah, you get whether, you know, you can check, cross check whether your answer is correct. Balance delay plus efficiency should be equal to 1 or equivalently 100, okay, as percentage 100. So for example, you know, balance delay, you have balance, you know, 57 balance delay, you have 0.226, and in the efficiency you have point, like, let's say we calculate this one. Exact value of the efficiency, 195 divided by 195 divided by 50.4 multiplied by 5. You get 0.773, 0.7738. So plus 0.7738. You see, when you add these two numbers, point 226 plus 0.772, so it is, so it's 1. Okay, so then the answer is correct. If you round it out to the nearest integer, you get 0.23. 0.23 plus 0.77, so then you get 1. So 23%, 23 plus 77, you get 100 as percentages. You see, so this is how, we check whether our answer is correct. So the other possibility is like, you can add the total idle time, 57 seconds, plus the actual work time, that is value added time is 195. So this should equal 252. So we got 252 by 5 multiplied by 50.4 seconds. So this is how you make this one. And then, reducing task time, split the task. By splitting the task, we can reduce the task time. Sharing the task, use a more skilled worker and work overtime, and also maybe we can redesign the task so that we can reduce the task time. Actually, we get the examination questions. Let's say this question, if we have the same question, it's in this one, you have been given this data. Let's say you have been given only this one, and then you are asked to balance the line for, let's say, 3 workstations because you have only 3 employees, and then balance the line for 3 workstations. Okay, so if the question is, you got this one, and you don't have this information. So in this example, we have output. We have output 500 wagon, and then available time is 420 minutes per day, per working day. So per working day, 420 minutes, okay, but then output is 500. So you have not been given output, and then you have only been given this one, and then you are asked balance the line for so then balance the line for 3 workstations. So then how we do this. And here only we have the precedence. And then we have total time is 195. So then we have total time is 195. So then we need to create 3 workstations. So then the cycle time and calculate the cycle time equals then value added time divided by number of workstations. So in this one, so then this equals value added time is 195. Number of workstations is 3. So then we use calculator here. 195 divided by 3. We get 65. So actually this is optimal cycle time. Cycle time for 3 workstations, okay? For 3 workstations. 3 workstation balance. But there is no gap. We cannot say that we will be able to. Okay. We cannot say we will be able to balance it for 65 seconds. So you can see if you can find a balance for 65 seconds, so then that will be great. But say without violating, without violating. So actually in practice, what we are not allowed is we are not allowed to balance the assembly line violating the precedence. So we are not allowed to violate the precedence. So without, it's not necessary unless specified to use the, the primary rule, the secondary rule that, I mentioned in this lecture. Primary rule as the primary rule is the most following task, and then secondary rule is the longest operation time. On the other hand, you can use longest operation time primary rule and most following task as the time breaking rule. That's a possibility. But then if you are asked, use this particular rule to balance the line. So if you are not being asked any rule, you are not being specified any rule, then you can create a balance without violating the precedence. So then actually you take down this question. You see, take down the question. Okay, balance the this line. Balance the line for 3 workstations, and then find balance delay and efficiency of the line. So that is one thing, and then you can also find what is the output of the day if working hours is, let's say, 8 hours. So then this is this question. Okay, you can you take down this question and next week I will discuss this answer for this question. Balance line, the same thing, okay. Balance the line for 3 workstations. Find the balance delay and efficiency of the line. What is the output of the output if working hours is 8 hours per day? Okay, you take down this question, this part. So balance the line for 3 workstations. Find the balance delay and efficiency of the line. What is the output of the day if working hours is 8 hours per day? So you can try to solve this question. next week, and then next week at the beginning, I will discuss the answer for this one. Actually, I have given questions in exams of this nature. Maybe I will discuss a similar type. You work this answer, you work out this thing, and next week I will discuss an examination question, and you can solve this one and tell me the answer. So now, if you have any questions, you can ask.
Normally, the minimum number of workstations should not be tallied to the actual ones, no?
Okay, what is the question you asked?
The minimum number of workstations should not be tallied to the actual ones, no sir, all time, because in previous one we calculated it as minimum 4 workstations, but when we actually calculated it, we got 5 workstations.
It is a good question that you asked. When we use this primary rule as the most following task having the most followers rule, then we got 5 workstations. So actually, if we had got 4 workstations, that means we would have got the optimal solution. So optimal solution is in the balance, optimal solution is 4 workstations. So if you get the 4 workstations, it means efficiency will be near 100.
Thank you, sir. Thank you. Clear.
You see, feasible task, number of works. Again, how to get the number of workstations and feasible tasks. You see, if you look at the balance, you see what I did. This is according to the without violating the precedence, right? So then, when it comes to I, let's say here, I comes into consideration after E has been allocated. So the CHI are candidates. CHI are feasible tasks, that means candidates. Out of them, we selected C because C is having the most following tasks. So if you look at the diagram, you can see C has number of following tasks, F, G, J, K, that's 4. On the other hand, out of HI, the other feasible tasks are HI. By HI are having J and K, that's 2. Okay. So CHI feasible, but C is most following, so C get the priority. So C is allocated. And then, you get FGHI, all are feasible. And then FGHI all have the same time. That's 12 seconds, you can see. F, G, H, I, same time. And also they have same number of follows, that's 2. So then we have tie break. So in the tie break, we select, we use the alphabetical order. And then on the alphabetical order, we selected F. We could have even selected I also, no problem, H, I. But we selected F. So then, you can see F was selected. But then HI had to go to workstation 4. GHI all have to go to workstation 4. So these students who asked this question, who is this person? Siva Tarshika Balasun something. Okay. Is it clear for you?
Yes, sir. I got the point, sir. Yes, sir.
Okay, right. So now, you work out the example, the exercise that I gave, and we'll discuss the answer next week. I will discuss an answer in the next week exam question also, remember, we don't always give you the output of the day. So if the output is given, we have to calculate the cycle time to suit that output. If output has not been given, we have to come to a cycle time, that is optimal cycle time. Then, after but once we balance the line, we are not sure whether we will get the optimal cycle time. So if we get the optimal cycle time, let's say on the 3 workstation scenario, if you get the optimal cycle time, what will happen is, your efficiency of the line will be very high. Efficiency will be near 100. So the idle time will be low, and so like that, So let's say we got the cycle time in the calculation as so here we got 65, right? So 65 means if you get a balance for 65, that means the efficiency will be near 100. But in the balance, if you got, let's say 68 or something, efficiency will come down to, let's say 80, 85%, some range. So, it's like that. That is for a 3 workstation. Okay, 3 workstation, optimal cycle time is 65. On the other hand, if we have been given a particular cycle time, then we can calculate the required number of workstations. That you can find by value added time divided by the cycle time. You will get the theoretical number of workstations. So that's how it is. Okay, then we meet next week. Next week at the beginning, I will discuss the example, one of the exam questions. Exam questions that were given in the last exam. So now that, okay, so we'll meet.
Okay, sir.
Okay, so
Thank
then
you,
I'm
sir.
going to end the class and see you next week.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.